Learning Measure TV, a science and engineering podcast with emphasis on measurement, brought to you by David Archer and LearningMeasure.com. Episode 26. Hello. I'm David Archer on LearningMeasure.com, LearningMeasure.tv. LearningMeasure.com is a subscription-based website, training website, associated with podcast. Students $5 get registering free access to courses. Student access after that, the access is $5 a month. Free. I'd like to announce a new course added to the course catalog. Instrumentation 201, like introduction to the following courses that will be one added to the course catalog. Signing up. Quality 152. I'd like to analyzer and intended to be Quality 153, Quality 155, QC Tools, Scatter Diagrams. As mentioned last time, Qual 154, QC Tools. Talk a little bit. Today we're going to continue on with that series on the 7 quality tools. On the 7 basic other things, basic graphing, and then we're going to data cover graphical format. And scatter diagrams. And I want to talk a little bit first before I get into that. This podcast series. So what we're going to do first is talk about a graph, what a basic graph is. And it's what a big graph. You have a normal graph. We're doing that is because that's part of to use the ability of the human brain to basically calibration techniques, see patterns, exam body of knowledge. You could have variables. One could be called latitude. One could be called longitude. Also, I want map. What you do is use that part of the human brain. We're going to feature reduce the free trial period to 1 week. For instance, so one of the things you can do is a normal. And because we really normally do is you have 2 axes, but I guess that's marked out. We also are announcing different units. North America, we're going to have some new ways that you can offset the cost of your subscription if you would like. Grids here. We are going to do something around where boundaries are. The same thing here. Get some feedback forms together. Make decisions. And if you're interested, are you inside this state? You can call the data. Send us an email. Graphically, could be map. Send an email saying temperature and length. We will randomly pick people where things are. How to point is you have, let's say, then you might people to send surveys. Course like okay, we're trying to get some first data x equal 1 interface. Of course, you want to follow our narrative. And we will pay you. And you can tell where you are relative to a map. You can navigate and look for things like surveys. Well, so basically, for those who are picked randomly, you can get your subscription paid for if you'd like. Basically, you might sort of plot another point. Plot another. You can have one grid survey representing. So if you're interested, you need to send me an email. And another and lines representing something else. So it's sort of a map. Or a map name, 0.5 is about here, and say that your boundaries are interested in taking part in the survey you're looking at. Now, in particular, graphic just kind of a few from there. So what I talk first there. And you can present data that way. What's a log? This is only going to be open to U.S. residents at the moment. You will probably expand this. It covers a wide range. One way of looking at it. So you go over to 1, 2, 3, 4. The log feedback from U.S. residents. Base 10, and you make a point. So if you're interested in if this is a line graph, you offset the cost of a year subscription. If you would like. You don't necessarily want to do that. You might want to also are interested. One thing about a graph like this, you want your units to be sensible. Like you don't want your points here, these tick marks as they're called. Things to be like 1.1 and so if you could, let's say you're plotting so 1s, 2s, 5s, 10s, some sensible unit, whatever it is. Same thing on this axis. Let's plot. Let's say. And sometimes they're making a grid. Today we're going to talk about filled in 3 of the 7 tools. The check sheet, the histogram, and the Pareto diagram or Pareto chart. 10, in which case they're normally called grid lines. We'll start out with the check sheet. 3 would be 1,000. What is a check sheet? Make a grid. The check sheet on this graph does this. So it's easy to make graphs on graph paper. That's what its function is. Numeric, not what's often done. Numeric data like temperature. In addition to these lines, you can although it could be range plot points on numbers in between. Of course, most people these days use computers to generate graphs. There's all kinds of tools out there. How many are in this category? NumPlot, come up with Excel, of course, different categories or classes that you're going to. There's a whole bunch of tools out there to just generate basic lines. You're putting things in. Now, what is a scatter diagram? go from one major scatter diagram to another. So this basically just it's meant to be a simple tool. Just a normal graph. A simple tally sheet's probably the simplest one. Okay, so these lines where data categories are, and then you just start counting the actual decimal number. Like I said, for instance, if you're a manufacturer of computers and all your computer models are named after fruits, 10, 20, 30, 40, then you might have a tally some sort of looks like this, where you're trying to find the relationship. Now, normally you don't label the axis 1, 2, 3. So what you would do, now again, the purpose for a scatter plot is to visually see if you can determine some sort of relationship. A banana model might have some problems. The axis where one simple data collection, for instance. Another graph here, the other's linear, might show an example, might collect data on two variables at once. If it's log and log, it's called a linear relationship. When you imagine noise in the manufacturing process, but it pretty much looks like a line. What we're going to do next, and you want to see this particular case, it looks like a line with positive slope. I mean, it's going from the lower right, so you might make a chart like this, lower left to the upper right, where you have a do that in that case. It looks like it's a line. The screencast format axis you have plots real machine, and then you have one variable. So that's what we're going to do next. We'll come back to defects more, and you total them. Just because two variables are correlated, that maybe that doesn't imply a causal relationship. Have a different problem. Maybe you notice. Here's an example. At the beginning of the week, some data. A set of everything's fine, but by Friday things are here's an example of maybe it is that graph on Monday there's no obvious correlation. Calibrates their machine, and by Friday the cal. Now, there may actually be, you don't know. It could be that the range of data that you took, recal their machines on Wednesday or something. But you don't know what the cause is yet. Wasn't wide enough to show the correlation. The other thing might be a location sheet data. Let's say, or there may actually be no correlation chairs data, and you wanted to find. You can't really tell from that. Characterize where defects. The other thing is you can. Here's an example of. Here's an example of a check sheet for doing that. Of course, there could be more complicated relations than just linear between data, and then you mark on the thing. And by the way, the negative everybody's experienced this who's rented a car from the upper left to the lower right. You see that has negative. There's negative correlation. Typically, when someone goes around with a check sheet on a car with you and walks around the car and marks the locations of scratches. But there can be more complicated ones. For instance, you might know that the data, or maybe you don't know, but you look at the data, you might conclude a check sheet. Like this set of data here. Other things is you can break up quadratic data into bins, or maybe a sinusoidal relationship between the two variables. You can't really say, well, how many defects. But you can actually do things like least squares fitting, determine things like what's the best fit parabola, what's the best fit sine wave through this data, and maybe you can learn something. So how the whole thing about clue sheets is they're supposed to be simple ways of collecting data. Now, what I wanted to emphasize, this shows correlation. It doesn't show causality. It's not the case that if there's a correlation between two variables, there's a causative relationship. Okay, how do you implement a check sheet? For instance, I'll give you an example. Well, first of all, you have to identify what problem you're going to try to investigate. If you have a gas station, you don't know what the problem is, and the gas station has a tree. Why is that? And you measure the diameter of the tree and the price of gas at the same time. Or something, but you need to write if you plot that on a scatter diagram, it will look like there's a positive correlation between the price of gas and the diameter. Like I said, there's more complicated tools. Does that mean that somehow the tree growth is affecting the gas price? Not at all. It's supposed to be very simple. The two variables that you're measuring are a function of another decide what time. From all the factors that could, gas prices tend to increase with time. You need to. And so does diameter of tree trunks, the number that you're actually going to. But there's no positive relationship. Once you have the categories, the tree trunk size and the price of gas. Collect data. So even though there might be a correlation between the data, one shouldn't jump to the conclusion that there's some sort of causal relationship between them. It might not be the case at all. To show causality, you have to figure out a mechanism. And if you can just show a mechanism, and then that the mechanism predicts the correlation you see, you have making a strong case that you have a causative relationship. Is training. That's a map. Now, first of all, basically everyone who's collecting data should understand why the data that you can do that type of probably should be part of the training. Chart on. Now, the one thing you should be trained in how to use the check sheet is if you have a chart, if it's so complicated that it takes more than, I don't know, 5 minutes, a scatter plot, this is probably too complicated. It's meant to be a simple process for collecting data. There may be a problem then. You need to make sure that your people may not actually be a line like that. What the defect is. It might be something else. It could be that they don't know how to recognize the defect. This is the units are too coarse in this direction. The important thing is they if you like expand this 10 times, understand something like this. That more than anything, you've got to make sure that they're trained in. So on a implementation, say, well, okay, once you scale is just too compressed. You've designed your check sheet, you decided what you're going to collect, you designed your check sheet. You need to expand the scale as much as you can. Implement the process when you plot the data. Then you're training so that you can see the first thing you should do is more clearly. A short run of collecting data. Now, what you do now. There's a lot of plots that analyze the data, and then you make any adjustments to the check sheet or to the process or anything. Let's say you have some process, and you want to check based on that trial run some variable in the process how you're as a function of time. Then you actually go collect the data. So this axis here is time. After you collect the data, interval that you take the data over. Some of the tools that you're going to use to analyze the data might be. And this is the variable, whatever it is. It could be length of a part. Once you've analyzed the data, rejects or something. Maybe the data indicates you have to do further investigation. Well, you need to look in to see why. And so you start plotting, and you say, let's say this is once a day, and today you get this value, and tomorrow you get this value. You have to do some sort of investigation, and then finally after that you have to act on your analysis. Once you've identified something, you need to and you get something like this. And you're getting some idea. You then repeat the whole process again. Variability. You need to know if the change you made the base process with time did anything. If you just have a lot of data, say 20 points, any progress, you really have or whatever. It's kind of arbitrary. So you can come up with a mean for the entire process. Now you've got your data, what you do with it. Well, the check sheet, you already draw that on the chart. Let's say this is the mean. You know that this is the data into bins. Well, the other thing you can now is determine A. You have statistical measures of the data set if you have a large enough data set initially. So what is understand your process? Well, you might have what are some sort of a 2 sigma limit. And you could also draw that on here, 2 standard rectangles. Let's say it's here. That's something you can do really quick in Excel. And you plot that on the and it may be different sizes. This could also be an arbitrarily set limit that you're trying to shoot for if you don't know the actual variability of the process. Now, this particular case, we're going to be looking at a continuous called the process where the categories are some sort of continuous data like, and this is called the upper control limit, weight. This is called the lower. Now that we've gone through that. So you could have only just numerical or just a lower limit depending on what you're trying to do. Histogram, but if your process is trying to keep number of as the value you've seen before in this podcast measurement, this will identify when things are going. There's the area of the rectangle is proportional to the uncertainty associated with the value. And usually you take some actual. Sometimes plot. There are other data for there are other lines in Graphical also statistics, something like the uncertainty associated with a line where the area under the curve. Now, one way of doing that. Now, the reason you're using what's called error bars, and then just set these too arbitrarily because it's a phenomenon. If you probability density have a process and determine the area by breaking it up into rectangles. Adjustments too often. All you're doing here in the case of continuous data is the opposite. You're generating these rectangles to come up with some approximation of a probability density experiment that shows that represents later podcast the range of values. But so what you call a control chart, and there may be other information on the chart showing. You could also have another set of variability of the data. Well, since this is areas exponential, one way of demonstrating if your plot detail is going to be basic control chart though has. They don't have to all line that represents the process mean, what number, and then an upper, a lower control limit, one could be really and then the data for the parameter that you're trying to monitor. Plotted as a function of time. Necessarily control chart is going to be n. That's one way of doing monitor processes. Another way of doing it in the bin divided by. Now, often you're going to present a graph. That pretty much. This is kind of be a short. This is only for continuous. All I talk about in this episode. So you're what you're. I should say something about the history. But one way you might do. Now this is probably more than you need to know to do a histogram. This was first described by. Basically, that's what it is. You'd have the area to represent Now, if your categories in a memo
data,
particular line, then what you calculate as a way to monitor process.
Something more.
And roughly the same time, that might be more important. Deming found out about Schubart's work,
in which case you
and added it to his.
Let's say your
data
was by machine or
now I want to point out
like that.
List of tools.
What you do then,
mapping thing we talked about before.
All the bases.
So this
the same
Schubart character is
in which case
I'm going to
cover one. I'm not going to cover it in
detail.
The
one of the
first
something that occurs
to advocate what's
called now
still a
histogram
process
control
measurement,
something called a Smith chart.
But you would do something like this.
Something called
now.
reflection.
So this is what
probably
Excel
not going to go and do another.
It's not going to finish. We'll break it up into
seventh
classes.
Cause and effect diagrams. I'm not going to do right away. I'm
for
going
passive
devices
in mind.
What I'm probably going to do next
always
for
passive
devices. I want to go a little bit further into
next time.
You
put list labels for the categories under here.
And notice I don't have the rectangle reflection coefficient. That can tell you at a glance by looking at a histogram like this, also called a bar chart. Because it's complex, it has an histogram where the bases so in a complex plane and in graphical format,
or let's say this is a real
part of the imaginary part. One of you guys,
when you draw this chart,
you separate real rectangles by some space. That's some visual indication that physical
is discrete data.
If you want devices or beyond the podcast coefficient, show yourself.
If you just look at a bar chart like this,
well, we also have the concept of
AP telling you discrete categories.
If you have a question, any question at all, my purpose here is not to introduce that. But it turns out, because
so what can you do with
questions, or you have some video you would like
complex reflection coefficient in terms of
ask a question or whatever.
As I was saying before,
feel free to do that. That's it for
with continuous range data, which I'll talk about now for a little bit. You can do more than with this data. This tells you
now if you take this in categories, and it's useful because it does tell you how the data is distributed among the categories. You can learn a little bit more from real and imaginary
continuous range of data.
On this
For instance,
chart.
you can quickly look at
what happens
the distribution,
is
come up with an estimate of the center and the
series
width. Like this particular one here,
circles
you're going to see the center is fairly obvious, and you can basically say what the width is. You can quickly see if there are any outliers.
Here.
If you see this nice bell curve, and then you got a point way over here,
if you drew
that's
them
probably an
outside
outlier
of
of some sort.
An
outlier is a point that comes from a different distribution. It may not be an outlier. It might just be statistically that basically every once in a while something's going to come out there. But maybe it's data that you don't really need to look at because it's not really part of the distribution you're trying to measure.
And then the complex part.
The other thing you can look at is the number of modes. Modes are
another set of circles that go
basically
this
peaks in the probability density function. It's local maxima of the
this type of chart.
For instance, you could have 1, 2, or 3 modes. Here's an example of a bimodal distribution.
Complex reflection plane.
It looks like there's 2 peaks to the distribution.
Contour lines that represent constant real part
that in itself does tell you something about the data set
overlaid on the chart. This is just another type of chart. There's all kinds of charts where you can put
the other thing
plot
you can look
things
at is something called
one
skew.
Here's
an example of a plot that has some skew to it,
or units,
which means basically the distribution is not symmetrical. It's sort of skewed to one side. Most of the data is on one side or the other.
There are other types of charts.
There's actually
this is just an example.
And I think we went over it in a previous podcast.
Data in this format.
There is a statistical concept called skew where you put a number to it.
The Smith chart is a subject I plan on covering in a few months.
You can sort of see real quick if the data is skewed.
But just give the idea, you can create these mappings.
Okay, Pareto diagram.
Various types of
first of all, I'm going to say a little bit about
another type of
Pareto.
And use that.
This guy's Pareto here. He lived from 1848 to 1923. He was probably best known as an economist.
That's pretty much all I want to
But he also did
about
other
in this
things,
episode.
Sociologist, philosopher, that sort of thing.
I will
He has a
talk
PhD
about
in
this
engineering.
later. So, but if you have any
probably best known
suggestions
for
about what
best
you'd like to see on the
attributed
podcast,
to him is
send
the
us an
80-20
email
rule,
suggestions at
where he actually sort of made
learnmeasure.tv.
the statement that
if you're interested in
about
if you have any
Italy,
question on any topic, science-related topic, actually
80% of the wealth was held
send
by 20%
it to me at
of the
questions at
individuals.
learningmeasure.tv, and we'll
That's
decide
what
whether
he
or not
was
to answer them.
basically famous for.
If you want to be on the podcast,
He was part of the government of
send your,
Mussolini,
email to vendors
and early. He did praise some of the accomplishments of the fascists. So he was.
Yeah, we've decided to move away from
although
the
he was not
quality
too
stuff for a little
happy
while.
apparently about
Probably not the
the
best choice.
curtailing of intellectual freedoms at universities.
A little bit more interesting.
I don't know. He was part of the fascist government.
At least I think.
And he wasn't particularly.
All right, well, see you next time.
Instrumental in developing something that's attached to his name, the Pareto chart, Pareto principle, and that sort of thing. Really, that's this guy, Duran, who lived from 1904 to February of 2008, so he just recently passed away. He's generally considered the father of quality. He sort of elevated the Pareto principle that, there's this thing called a 20-80 rule, which is sort of pseudoscientific thing that, 80% of your effects are caused by 20% of your causes is generally how people think about it. But Duran, basically broke the data into what he called the vital few and the important many, and in between was the awkward zone. But we'll talk about that in a minute. But Pareto's the one, or Duran's the one who elevated the Pareto principle to something that could be in quality. He's the one who basically was popularizing the Pareto chart. It wasn't really Pareto. It probably should be called a Duran chart and Duran's principle. In fact, now they've gone to calling it Duran's Pareto principle. It was really Duran who was the one who was responsible for this, but that's an aside. Okay, now, what a Pareto diagram is you start with your histogram. It's basically a histogram, except what you do is you sort the rectangles by, in a Pareto diagram, you're going to go equal bases, okay? So you're going to sort them by size, so number of counts. So what you're going to do is you'll take all your data and then you'll, well, hopefully they're all the same size. Excuse my drawing ability. And so it's monotonically just decreasing. And then so this over here, axis over here, you're going to have your category names down here. Let's call them 1, 2, 3 just for, but they could be anything. This could be, color or weight or some such thing. And the weight, in this case now, this axis is going to be counts, So this will be like N1, this will be N2, whatever this is. Okay. N3 all the way down to whatever, which is the number of counts in each bin. Then the next thing you do is you come up and you add up all of them in all of them, you come up with some number, N total. It's going to be N1 plus N2 plus. And then you compute, for the first bin, you compute N1 over NT times 100 to get percent. And on the other side, you have a chart that goes from basically 0 to 100%. And let's say this was, I don't know, 10% of the data. Let's say this first one is 10%. So you'd go, well, okay, that's about 10. You'd plot that point here. Then you go, okay, for this one, you're going to want a cumulative total. The next plot you point is N1 plus N2 over N total times 100, and then you would plot that point. Okay, and then the next point you would go N1 plus N2 plus N3 divided by NT times 100, and then you plot that one. And you can get the general idea, then you connect the dots. So it might look like this. So that whoops, made a mistake here. obviously it ends at 100%. So then you connect the dots. And that is your basic Pareto chart. Of course, that's probably not how that looks for this data, but you get the idea. Now, what Duran wanted to do is separate the data into what he called the vital few and the important many. And what you do is you look for knees, which are places where slope changes happen. If you look at here, this sort of somewhere, if you sort of look at the graph, there looks like there's like two slopes here. And this region right here, he would have labeled something like the awkward zone. But in here, this is you draw a line here. Everything to here is the vital few, and this way is the important many. And the whole idea is you want to spend your time solving problems on this side, not over here. It's not often the case that a Pareto principle will be involved. In other words, that the majority of your effects are caused by a small number of the causes. This data actually, if you look at this data, it doesn't have that property. But there are some data sets that do. And what it does, what the Pareto diagram does for you, is it tells you where the most important places to look. You know, where the biggest return on investment in your investigation is going to be. That's the real purpose of the Pareto chart. So, and Pareto analysis is to basically identify what those causes are. Okay, that's it for this week. That's what I wanted to talk about. Next time we'll continue on with this series until we're finished. But we really do have an interview scheduled. But it might not happen by the next time. So if there's an interview, there might be in there. Also, so if you have any suggestions for what you want to see here, send us an email at suggestions@learningmeasure.tv. If you have any questions that you'd like answered, you could even do a video question. We'd love to get a video question, or even a suggestion. Send it to questions@learningmeasure.tv. And if you want to be part of our consultant network, or you want to be on the podcast to show your product or whatever, or want to just be on here, do a technical talk, or even if you're, like I said, near retirement or retired and would like to pass on your knowledge, send us a call at vendors@learningmeasure.tv and tell us what you have in mind. That's it for this week. I'll see you next time.